So probably in the last lecture, we are not continuing through the classification of relations. So here we'll really recover what we left in the last lecture. So first is I introduced 5 relationship. Maybe the first three is most basic, reflexive. That is the element that goes through itself, and also transitive is like x to y, y to z, then x to z. And symmetric is x to y, then y to x. So these three are the basic for other deducible from relation 4 to relation 9. So and then inverse, I don't think this is relatively important to other. So if you just can remember, I will show you one example later. And equivalence is if the relationship you find in the relationship set, there's all of the reflexive, symmetric, and transitive, then it must be equivalence relation. And there's a special denotion. So the first new relation we talk about is the anti-symmetric relation. That is for all x and y in a certain set S. If x related to y and y related to x, then there's only one possibility that x is related to y. So what does this mean? Let's think about what is called anti-symmetric. So it means it should not be symmetric, right? So in the symmetric relation, we say x related to y, then y must relate to x. And here it says if x is not equal to y, then x is not anti-symmetric with y. And then x is not related to y. So yeah, so x related to y, y related to x cannot coexist at the same time if they're not equal. This is anti-symmetric, which means they are not symmetric. Okay, and let's see the last two, partial ordering and total ordering. So from my view, there's two very good examples showing that partial ordering is like smaller. You can say partial ordering is smaller or equal to, and total ordering is just smaller. So I will show you why that makes sense. So let's see first the partial ordering's definition. So it's reflexive, anti-symmetric, and transitive. Then let's think about what it means. So first, it means like x related to y, y related to x means x related to y. So that means x is equal to y. So that means at first, it should satisfy this condition. Then transitive means that it is transit to another than another. So smaller equal to or equal to makes sense because if x smaller or equal to y, y smaller equal to z, then x smaller no y smaller equal to x, z smaller or equal to y, then z smaller equal to x, and this is transitive. Is that reflexive? Yes, because for all real numbers like x is smaller or equal to x because x is equal to x. So smaller equal to or larger equal to makes sense here. And for the next one, why total ordering is smaller or larger? Let's think about it. Let's first see the definition. It means like for x, y, x related to y or y related to x. So it cannot occur at the same time, which means like for example, a smaller than b and b smaller than a cannot occur at the same time because it's or, and this or is not the it's not like means both occur can make sense. This is the exceptional. Okay, so this is the total ordering and the partial ordering, and it seems like it's you can gradually get a sense of it, but I don't think total ordering and partial ordering is important in the definition because we'll see many of them later. So what you should supposed to know here, I think most important is equivalence and first three. And this ordering, well, we will review it in the real numbers definition. That's possibly 2 weeks from now. Okay. So let's consider some example. I'm sure you have played a game. It's called Caesar Rock and Paper. So in that game, like it's a circling beating relation. Like rock beats Caesar, Caesar beat paper, paper beat rock. So yeah, seems like we have talked about in the last lecture. So this is the example of it. And yeah, so this symbol we might also see it before, like if x is parent of y is a parent of x, then they are inverse. They're inversely related. Okay, sounds good. So let's see the new example. So for animals in the zoo. So let's first define the here. The waveline uh means the same species. So let's check out if that's what kind of relation that is. So first, like consider the example of what animal I like the most in the zoo. Possibly it's a zebra. I like a zebra. I like their color. So let's say zebra. So if X is a zebra, then X itself is a zebra. It cannot suddenly turn to a hippopotamus. So it's reflexive, absolutely. Then if X is a zebra, then Y is the same species as X, then Y is also a zebra. So which means zebra, they are the same species. So it's also symmetric. And third one might be very intuitive as well, like a zebra, a Y, same species, and Y, same species, Z, same species, then they're all zebra. So X and Z are the same species. So we are solved this one. Okay, the next example is, let's see what's the next example. So here is more abstract. It's not like a children's game. It's not like a zoo, or it's not like parent-child relationship. So here is an abstract one. Let's say S is a certain set. It contains the element 1, 2, 3, and R and R's relation. Oh my God, it only has two. It only has two relations pairs in it, which is 1, 2, and 2, 1. So from here, we can definitely see it is symmetric. It's a symmetrical relation because 1, 2 for all elements in it, like 1 related to 2, 2 is related to 1. So they satisfy the symmetric, but it's not reflexive because 1 is in it, but we do not observe 1, 1. So yeah, so 1 is not related to 1. See here. So that's why it's not reflexive. And is that transitive? No, because 1, 1 is not 1 related to 1 is not in it. This is because like if you 1 related to 2, 2 related to 1, then it must be 1 related to 1. And this is not satisfied, so it's not the equivalence. So this is our third example. So let's say the last example. So it is just recover what I said before when we are doing the partial ordering relation. So smaller or equal to is a partial ordering because x and y, z, for all of them related to R, they all belongs to R. Then x smaller or equal to x, x smaller to y, and y smaller or equal to z. Then x is smaller or equal to z. So this is transitive. This is reflexive, symmetric, totally, because when they are not symmetric, anti-symmetric. Anti-symmetric is totally fine because if x smaller equal to y and y smaller to equal to x, then it must be x equal to y, and this is defined in a real number. All right, let's return to some new material. First is called relations closures. So what's the relational closure? So we have seen that before, like in this example, it is not uh, reflexive, right? They said it's not reflexive, but how to make the relation reflexive? We might add some new element to the relation set. If we add 1, 1 and 2, 2, and 3, 3. And this relation R becomes a reflexive relation. And sometimes we just denote the set of it. And to do it, we just do the union. This set with this set, we do the union. So it becomes a reflexive one. So this is just like the definition of a closure. Let's see in this example. So for all set A of x, y, they just consist of the Cartesian product in set S times S, Cartesian with X. So if it's union with another set B, can make A union with B a relation R on the set S, then A union with B, notice that it's A union with B, not single A. A union with B is called an R closure of R for S. So this might be a little bit confused, like there's so many R closure of R for S. So what that mean? Let's see the example below. So let's say S is 1, 2, 3, 4. R it contains 4 pair relation 1, 2, 2, 1, 1, 1, 2, 2. Then while S is symmetric for all X go to Y, Y go to S, and they are self-symmetric as well, right? They are self-symmetric, like go 1 to 1, 1 to 1, 2 to 2, 2 to 2. So that's it. Is it transitive? No, because let's say whether it's transitive at 1 go to 2, 2 go to 1, 1, 1, it is in it. And 2 goes to 1, and 2 goes to 1, 1 goes to 2, 2, 2 in it. 1 goes to 1, 1 goes to 2. Yeah, so it's actually transitive. It's actually transitive, but it's not a reflexive. This is 100% sure. It's missing 1. It's missing 3, 3, and 4, 4 here. So, but if we define a new set called R1, the new relation R1 is the union of set R with set 3, 3, and 4, 4. Then R1 is the reflexive closure of R. So this is this total set, the total union set is called a reflexive closure of R on S. So if the so combined with the closure, what's the if the new relation is reflexive, then it's called reflexive closure. If the new relation is transitive, then we say it's a transitive closure. If the new one is well ordering, is a totally ordering relation, then we say it's a total ordering closure of R on some set as A or B. So this is how we define the set closure. Yeah, we can see another example. Let S be partially exposed stones in a stream. So this means like you are jumping on a set of rock, on a set of stones in a stream, and the river is flowing there. So so let's define x a wave to y, which is like the water wave. So which means you can jump from x to y without getting wet, which means you are not fall into water. So the distance is within your control, right? So let's say it's reflexive. So like you can drop, you have to jump at least 0 millimeters because you are jump up and fell down and you are on the same rock. So that means it is reflexive and symmetric. If you can jump here to there, then you can also jump there to here. So just imagine like the stream is actually flat. So there's no elevation difference. Like there's the stone here and the stone here. So you can jump here to here, but you cannot jump back because of gravity difference. We're not considering that. We just consider the distance difference. All right. But this new relation is not transitive. This is because imagining like if you can jump x to y. So let's draw a graph. If you can jump x to y and y to z, this is z, this is y, this is x. This distance you can jump to, this distance you can jump to, but this distance is not sure because it's longer than both. So it's not transitive. But now we're defining new relations that is look like that. And x relate to y, which in the new relation means you can jump you can step x to y, you can step x to z in the sequence of steps, which means like you are not directly jump to, but you are jumping some like intermediate step, then go to it. Then it's a transitive closure because now you make sure it's transitive, because the sequence you don't define how long the sequence are. It can be very long. So you can always make sure you can jump to, if you make sure you can jump from x to y and y to z, then you just take x to y to z as a sequence of steps to get to your final position. So that's the logic of it. All right. And then we'll see the next example. Next definition is the equivalence class. So every equivalence relation on the set can create a class of something. So this is called the equivalent class. So the definition is like that. And this one is a equivalence relation on set S, then the set of all elements that related by this thing to a given element S, X forms the equivalence class of X, defined by X. You just do the squared bracket outside of it. It is equal to all of the element belongs to set S, while it is equivalent to X by an equivalence relation. So this is its definition. Let's see one example. So set S is here. This is set S, and the age, some like very fat age, means for all xy in the set S, then they're in the same block. Yeah, they are in the same block. Like this is one block, this is the second block, very tiny, and this is the third block. So this is block 1, block 2, block 3. Well, and then we need to prove like this is an equivalence relation, but it's very intuitive. You can prove it by yourself. Just prove it's reflexive, symmetric, and transitive, like in the same block. Then a set is always in the same block. So reflexive, symmetric, symmetric if x and y in the same block, y must be in the same block with y, so symmetric. And transitive, x, y, same block, y, z, same block, then x, z must be in the same block. So it's a equivalence relation. And let's see what's the equivalence class mean here. So let's say, well, 1 is related to 2, 1 is related to 4, but 1 is not related to maybe 5, maybe 6. That's not related to. Okay. And yeah, and we can say so what's the equivalence class defined here? Let's say 1. What's the equivalence called 1? It has 1 to 4, right? Because that's all of the elements in the set S that's in the same block with X, which is related to X when X is 1. So which means like the equivalence class 1 is equal to equivalence class 2 equals to equivalence 4. And that's the equivalence class. And for 3 and 5, they're in the same equivalence class. And 6, they're in the same equivalence class. So that's so this example illustrates its definition very well, I guess. All right, so let's turn to some different material. It's still like a very good connection with the last lecture slide. So if this is for all equivalence relation, and the equivalence class X, if it's not equal to Y, then their intersection is empty. So this is very similar to our definition of a partition, and we'll definitely show that it is actually a partition. So we'll first prove by a contrapositive strategy. So if you want to prove if x not equal to y, then their intersection is empty. Well, first prove if their intersection is not empty, then it must be x equivalence class of x is equal to equivalence class of y. So let's prove this one. Let's prove this one. So for proving the statement 1 here, what strategy I will use is to, well, because we are proving equal, then we'll first show it's X equivalence class X is a subset of equivalence class Y, and then do the vice versa to prove the equivalence class of Y is a subset of equivalence class of X. Okay, so proving the subset relation, we are doing yeah, subset is also a relation by our definition here. So if we're proving subset, we are first supposed to like for all of the elements in set X. And because it's not empty, then there exists one element, at least one element that belongs to X intersection with Y, right? So Z is existed. Then Z is both in X and both in equivalence class Y by intersections definition. Okay, so what happened is that X is in X, Z is in X, so they are related because that's the equivalence relations definition. When they're like, if and only if they're equivalent to each other, then they are in the same equivalence class, right? And this one is also true because Z is in Y. So there must be an element Y in equivalence class Y that Z is equivalent to. So these two relationships make sure like X is also in the equivalence class of Y, which I do not write it out explicitly, which means X is a subset of Y equivalence class. Okay, and in the opposite direction is very similar because for here we define Z and for another W, they're in the intersection of it. And for all Y that belongs to the equivalence subset Y, then what happened is like W related to Y based on here, and W go to X here for all of the X in the equivalence set of X. All right, so then Y is equivalent to W equivalent to X. So Y is also in the equivalent set of X, which means like which we prove the subset in both directions, so that it must be equal. So Y is proved by the contrapositive strategy. We prove the theorem. Okay. Do you have any questions here? Okay, sounds good. So we'll move to the next one. So this might be, we might call it a lemma because we use this theorem to prove the next important theorem, which calls the induced partition theorem. As you can see before, like you can see before, the definition of the equivalence class is maybe it's very similar to the partition because you can see here, the equivalence class is just a partition of set S, right? So here, the induced partition theorem is saying that for all equivalence relation on a non-empty set S, the equivalence class induced by the equivalence relation is just a partition of S, and we can denote it by its notation. So how to prove it? So to prove it's a partition, we need to prove two things. Is that like for all I not equal to J, Si and Sj as their blocks, their intersection is empty. So this is first we'll show, and second we'll show is that the union of all of the partition blocks is equal to the original set itself. So if you can prove these two things, then we definitely have already proved the theorem to prove it's a partition. So first, by definition of the equivalent class, then this is definition because let's see here. Okay. No, not here. This theorem prove like the equivalence relation, and if it's not equal, then it must be empty. So the first property of the partition set is already being proved. Okay, and for the second one, you need to prove like the union of all Si is equal to S. So first we'll show, because like each Si for all I in the index set of capital I consists of element originally in S, which means it cannot go beyond S. So in this situation, it is the union of all of the Si, the union of all of the partition blocks. Maybe you can call it partition here already. So there must be a subset of S. So here we prove the one-way subset, and we'll prove the second-way subset as in the second part. So so the second part will show like S is a subset of the union of all Si. So it might seem like very hard to imagine, but you can use the relations property. You can use the equivalence relations property as it is reflexive. So reflexive means X must be in all of the Si because X is related to X by reflexive property. So all of the Si, there must be one X. Okay, so for OX X in a set S, then what we can find is like there must exist one I that is in the set capital I, such that X is in Si. And this means like there exists relation means the union of the index set Si. So by 2 and 3, we proved the equivalence of the original set with its union of the partition of the equivalence class. So which means like it is a partition combined with one together. And we can see one example here. It's like this example is actually, we'll see, when you use the graph representation for all of the relations, so that it can be more like more visualizational. As we can feel before, like we are talking about all of the relation. We are doing the set, but set is not very obvious. Set is not obvious to human's eyes, but graph is. So let's say S is 1, 2, 3, 4, 5, 6, and the relation will be this huge set. Again, you can imagine how huge it is. You may not read once and think about it, what it looks like, but it's actually partitioned set S into this one. So the equivalence relation make the equivalence classes as those, and they're actually a partition of the S. Right, so this illustrates our previous examples well. So how we can make this into a graph? So the graph, we may not already talk about graph because graph is very complex in mathematical senses. So we'll first informally talk about graph representation. Okay, so each of node here is an element. So in the graph, like this is a blank paper, and all of the points is an element in the original set. 1, 2, 3, 4, 5, 6, as you can see here, right? So that's you can first point out some random points as the element in the set S. And then if you can see here, if one of the relation occurs here, 1, 1, 2, 2, 3, and you drop a directed arrow, or we say the directional edges as it goes to 1 to 1, maybe 1 to 2. So you draw 1 to 2 here, and 2 to 1, 1 to 3, 3 to 1. This is wrong, so it must be going in the wrong direction. Yeah, something like that. So here the element is called vertex, and each of the arrows is called a directional edge. And so we can see how the graph looks like. If there's like 2 arrows between them, then they are related by they are related by the equivalence relation. And maybe 1 arrow means like they are related by equivalence, but if it's not in a one counterpart with another one, then it is not symmetric. So that is how we use the graph to illustrate the relation, and especially the equivalence relation. Yeah, and also notice here you can miss some like curvature directional edges, and those are reflexive because it goes to the element itself. And we are talking about another theorem, which is the inverse partition theorem. So previously we talked about like an equivalence relation on the set. If they can produce equivalence classes, then all of the equivalent classes are partitions. So in this theorem, it says like if there is a partition on some non-empty set S, then it can induce one equivalence relation. And this equivalence, it means like X and Y belongs to same block produced by that partition. Okay. So when we are going to prove like this is prove something is a equivalence relation, we'll prove it one by one by their property: reflexive, symmetric, and transitive. So for all of the non-empty set S, let's use this to denote this a partition. So we are gonna to prove this in this theorem called the inverse. So the previous theorem is called it's called induced partition theorem, and this one is called uh inverse partition theorem. So now we are going to prove the inverse partition theorem. All right, so for all of the non-empty set S, if we can use this to denote a partition on it, then for all x not equal to y, it is empty. The intersection is empty, and this is illustrated by the partition property, and also the union of the SI is equal to S. Okay, so why we can tell it's reflexive is because for all of the x in each block, it is related to itself, right? It is in the same block, so this means all of the x are reflexive. So prove what? Prove the first reflexive property. All right. So let's see the second and third one. So if x, y in the same block, then x is related to y because they're in the same block, and y equal to x because they're in the same block. So it's symmetric. And for the transitive, if x and y in the same block, y and z in the same block. So maybe I'll first to do a very small counter-positive proving strategy here. So suppose x, y is belong to Si, and y, z is belong to the block Sj, and Sj is not equal to Si. So what will happen here is like, then there must be y in the intersection of them because it's not empty, right? It's not empty, and they're not the same. If they're not the same, then it's not empty. But y is in both of them, so it must be not the same. It must be non-empty, so it be the same. So so this means like I is equal to j. I is equal to j. And this is because we do it reaches a contradiction. If xi is not equal to sj, and then it is empty based on the previous lemma. So y is the element in it, which makes it non-empty, and the non-empty situation, which means like Si is equal to Sj. So X and Z is in the same block. So we proved from these two, we proved X also related to Z. So we proved it. Okay. And this is nearly done for our exploration of the relation, which is slightly complex because we introduced 8 relations here, and maybe 9 and 10 if you look at more advanced book. Relation is always very huge topic to talk about. And we'll end the relation with the last example. So we say we can put integers partition to 3 blocks, Pn and the set of 0. So this is very reasonable partition because we make it positive numbers, negative numbers, and 0, which is not neither positive nor negative. And actually it's induced this partition because the previous inverse inverse partition theorem says like all of the partitions will induce one equivalence relation. So what is the equivalence relation it induced here? So actually, if we consider the property of P, N, and 0, then X and Y have the same sign as the induced equivalence relation, because all of the elements in P, N, and 0 have the same sign. And when they are crossed, it must change sign. Or you can just say 0 has no sign of positive nor negative. So yeah, so this is the new equivalence relation it induces. So let's go to the new topic. We are done with the relation, and we are talking about mathematical induction. This is very important proving strategy. I would say in the same position as contrapositive, direct proof, and proof by contradiction. And there's also one new proving strategy we'll talk about today, which is called the proof by mathematical induction. And the prerequisite for that is the set, is a set theory, and also some principle, some axiom called well-ordering axiom in natural numbers. Okay, it says like every non-empty set of natural number has a least element. The least elements here means like it's the smallest natural number. It is good to give example like consider set 1, 2, 3, and you can say 1 is the least element here. And if there's a set like 1, 1, 2, 4, 5, then it's equal to 1, 2, 4, 5, because the repetition is not allowed in the set, and you cannot and you should not consider that. So 1 is the least element. So always seems like natural numbers has a least element. It makes sense. And this is largely because of like the natural number is bounded below, is bounded by 1. It cannot go smaller than 1. But for integers, it cannot always make sure there's a least element, because it can go to negative infinity. So you cannot always make sure 1 is a least element. And or like negative 1 million is the smallest. Possibly there's negative 1 million and minus 1. So you are not always going to figure out, but a natural number has this property. So the corollary is that if set A has at least one element, then there exists X belongs to A such that X smaller or equal to Y for all of the Y in A, and Y also is a natural number. So this statement, natural number, is very critical here. Somebody might forget about it. And if you forget about it, it doesn't make sense, because sometimes Y is an object, it's a cat or a zebra, that it cannot say like there's a least cat in some set, right? Okay, and we'll talk about one notation, like Pn is a statement like the integer n has property P. It's not a power set. It's like the P we're talking about at the first lecture of set, like it's a property of something. So the integer n has a property P means this. All of the examples and theories we'll see later. Okay, and we'll see the principle of mathematical induction's definition formally here. So imagine n0 is a non-negative integer. Usually it can be negative, but it can be so negative. Like if it's in -1, -2, and it's ends at -2, then it makes sense. We just make sure it not goes to infinite negativity. And P is a propositional property. Oh, well, if this propositional is important, it can be important, cannot be important, depending on the context. But in this level, we'll just say, well, if it's a property, then it goes well. Then suppose P n0 is true, which means the non-negative integer n0 has the property P. So this is maybe we'll say is the first statement, because this is statement, it says the integer n0 has property P is true. And then the second statement we'll make is that, well, first suppose Pn is true for all of the n0 smaller equal to n. smaller or equal to k, and k is all of the integers greater than n. So we'll draw a number line to represent this. So this is n0, and this is k. K can go very large. K can go very large. And for all of the n, these are all n. N between n0 and k is satisfy property P. Okay. And then if this is true, n can equal to k, and p k plus 1. So there's always k plus 1. K plus 1 also holds for the property P. So this statement is a conditional proposition. If this conditional proposition is true, and combine this is 2 and this is 1, and if 1, 2 both true, then Pn is true for all of the integers greater or equal to n0. And remember, greater or equal to is a partial ordering. It's not a total ordering. Okay. So this definition seems very difficult to understand. I don't know. It might be very it might be very good. So why not see example to see why it's actually working? This is proof I write about. This is proof I write about, like how to prove it. I would say just prove it by contradiction. So first, suppose like P n0 is true, and for all of the k greater or equal to n0, and we'll return to this later. But first, we'll see the example. So how to use it? So use mathematical induction to prove 1 plus 2 plus 2n is equal to n times n plus 1 divided by 2. So this is a very famous formula. I would say most of you see it in the school before. So we'll do it in two different, maybe I'll just do it in a mathematical induction. Okay. And another one is like you use like 1 plus n, and to find like 2 plus n minus 1, and that'll be very, very difficult if the n goes too large. So we'll not consider that. I will just use mathematical induction to do it. So first, the first case is like n0 is equal to 1. So in this case, 1 plus 2n is just 1. And 1 is equal to 1 times 1 plus 1, which is 2 divided by 2 is 1. So condition 1 satisfied. And for condition 2, we'll say if 1 plus 2k for all of the k greater than 1, if this satisfied, then k plus 1 will show that this is actually true. So, well, this can be easily done. This can be easily done by using this property. So we wrap this all together to change to this one because they are equal, and to add k plus 1 to the numerator and becomes this one. And then the next step is to form some strange connections, is to do a factorization. So this becomes k squared plus 3k plus 2, and this is by factorization is k times 2 plus k times 1, because 2 plus 1 is 3 and 1 times 2 is 2. So it comes in this form. And notice like k plus 2 can be written as k plus 1 plus 1. So it's in this form. So we have to prove it. So since we are done both the like the n0 case here, and this is like suppose k and prove k plus 1 case here, we're done both conditions. So we can say the statement is already been proved for all n greater or equal to n0, which is 1. Okay, so we have seen this. We have seen this in a very short time, and we'll go back to see why mathematical induction is true. So now I think you get a sense of how mathematical induction is worked. So why it's true? We'll use the well-ordering principle again, which is like said a set of natural numbers will have a smallest element. So first we'll define it. Define two statements. So one means the n0 step, and 2 means the k plus 1 step. All right. So suppose there exists one m greater or equal to n0 such that Pm is false. Because when we are doing the contradiction, proof by contradiction strategy, we always assume like there's some not working situation. So if for all n not greater or equal to n0, all of the it is not the case that all of the n work for property P. So there must be some element Pm doesn't work. And because m is a natural number, so by the well-ordered principle, there exists t greater than 0 such that m is equal to n0 plus 1. N0 plus t is false, which means like p n0 plus t is false. And the t is the smallest integer and not smallest integer, natural numbers in this case. But you can also say it's an integer because natural number, and in this case t must be positive, so it's an integer it's a natural number as well. Okay. And this means like for all n0 smaller equal to n smaller equal to t minus 1 plus n 0, Pn is always true. Yeah, this makes sense because this is the smallest integer to make it not true. So if it's smaller than it must be true. Then here it encounters a contradiction. The contradiction goes like this because by two here. So notice we have used 2 here. Okay, this is 2 because by 2, if pk is pn is true, like pn is true for like all between all n0 and k, and we can consider n0 is here and k is here, and if for all n here pn is true, then pk plus 1 is true, and pk plus 1 is k is equal to t minus 1 plus n0, and plus 1 again, we get cancelled with the negative 1 here, and we get t plus n is true. And well, this is a contradiction to what we supposed before, like p n plus t is false, so it reached a contradiction. So it must be our assumption is wrong, and the mathematical induction is true by the proof by contradiction. Okay. All right, and there's some other examples, and you can, well, I think this one is interesting. This one is interesting. It's like using mathematical induction to prove the set with n elements power set has 2 to the power of n elements. Remember, we have talked about the power set, right? Power set, we say, well, at that time I say we cannot very rigorously prove it to have 2 to the power of n elements. But after we studied mathematical induction, we can give a formal proof of why it has 2 to the n elements. So we'll do 2 cases, like also a definition like one here. The one here is called base case, and 2 is called inductive case. So we always say this is base case, this is inductive case in later examples. So in the base case, is n is equal to 0, so which means it's an empty set. And empty set contains one element which is equal to 2 to the power of 0, which is 1. So basically it's proven. And for inductive case, inductive case, we'll suppose like all right, so first suppose like S contains k element and it works for and the statement works for k. So PS has 2 to the power k elements. This is true statement. Oh, wait a minute. Okay. So this is true statement. And we want to show this one. We want to show the T, which contains k plus 1 elements, have 2 to the power of k plus 1 elements. Well, so somebody will say, if we already have S, can we add another element to it to make it so it has k plus 1 elements, so we can prove it? Well, that's not general enough because S, if we just add one element to S, we might reach a condition like the k plus 1, the set with k plus 1 element is conditioned on S. So it must have the same element as S before. But we here will be very general to say all of the k plus 1 elements. So yeah, so it cannot be only S. So we must suppose an entirely new set T which contains k plus 1 elements to prove it. So because T can be written as T, yeah, here we are decompose T. T is to decompose into T, get rid of T and union with T again. This T is equal to this one, right? And T, if we get one element off, how many elements it have? If it has k plus 1 elements, so now it has k elements. So P, so the power set of T, get rid of T, has 2 to the power k elements. So now we're adding the getting rid of element T into it. So we are taking union with it. So how many new set it forms? It forms 2 to the power of k new subsets. Because all of the elements in it, like suppose there's like A, B, C, right? They only have 3 elements, which is impossible, it's too small. But imagining there's only 3, that's a set, and it adds a new element D here. So how many new set it forms? Like it forms DA, DB, and DC. And also like DAB, DBC, DABC. So there's 6, which is the total number of subset. So every subset of the set ABC will form a new subset we consider with a union with D. So there's 2 to the power 2, 2 times 2 to the power of k, which is 2 to the power k plus 1. And why we times 2 is because originally it has 2 to the power k elements. This is the original. And when you add an element t back to it, will form 2 to the power of k new subset again. So we are adding them together is like times 2. So this is how we get it to the end. All right, I think that's basically the proving idea for this one. So if you are done with this 2 part, and you show like for all of the n elements that has 2 to the power of n sets by multiple condition, because we're setting the n0 to be 0, and this n can be for all of the n greater or equal to 0. Okay, and let's talk about one more example. So the more example is like for all, and yeah, this one is very similar to this one. It's using numbers to prove it. It's very similar to this one, but it's in a different strategy. We'll see it. So you are dealing with numbers. I think most students like to deal with the numbers at first because they have very strong background, like algebraic background in high school. So they like to do number questions. Okay. So for all n, which is an integer, and n is greater or equal to 0, the number 4 to the power of 2n plus 1 plus 3 to the power of n plus 2 is a multiple of 13. So multiple of 13, how do you define it? We define multiple of 13 like if A is multiple of 13, then it must be written as 13 times the number of B, and there exists the B in the set of Z. So if we can prove this one, then we say A is a multiple of 30. All right, this is actually a definition we'll see in number theory, or in the modulus theory, but well, first to define here so you can understand how we'll prove it. So the base case is very simple. Base case is like n greater or equal to 0, so we just set n equal to 0 to say to look how it goes, and it goes like 4 to the power of 2 times 0 plus 1 plus 3 to the power of 0 plus 2, which is 4 plus 3 to the power of 2, 9. And this is 13, which is equal to 13 times 1. So this is a multiple of 13, there's no doubt. And in that case, like suppose we have this is true. We have the true as this is like 13 times something m, for there exists a m in a z. So here we are suppose the k for all of the 0 smaller or equal to k smaller or equal to n, it works. And k is is an element in the integers. So in that case, we first assume this is true, and we want to show if k is replaced by k plus 1. This is also a multiple of 13. Notice here I made a small mistake here. It's not a mistake, it's just a mistake in the writing form. So 2k plus 2 plus 1 is actually equal to 2k plus 1 plus 1, right? So actually it's good. But this is better for understanding it later. So I'll write it in this form. So remember this one and I'll erase it. Okay. So how can we deal with this one? So this one we can first to separate form. So separate form into remove the 2 out. So it's like 16 times something, and remove this 1 out and 3 times something. And there's one very strategic move here is to plus a term and minus term, so which is 0, but we just add and minus them and cancel each term out. This is because we want the like the final form to be something like 13 times something. So we want to make sure we will use this fact, we'll use this kind of number in the end. So if we plus a 16 times 3 to the power of k plus 2, we have the 3 to the power of k plus 2 form. And if we are minus something here, and we'll have this term again, which is exactly what we want. So now we'll combine all of the 16 time together, which is 16 times this one. And this one, look at that. If we 16 is equal to 4 to the power 2 k plus 1 plus 3 to the power of k plus 2, which is exactly multiple of 13. So we can write this here. And what's left? So this term is, so what's exactly happening here is we are separating 16 out, and we are cancel these 2 terms, right? So yeah, so this term and this term is canceled out. So this is the remaining one. And remaining one, we also have 3 to the power of 2 k plus 2. And what we left is 3 minus 16. Wow, this one is 3 minus 16, which is negative 13. Negative 13. So we are reaching this form in the end, which like 13 times 16m minus 3 to the power of k plus 2. And m is an integer, so it's also a multiple of 13. So we're done here. Sounds good? Okay. So maybe I think the most difficult part is this part. If you can always think about some tricks in this kind of mathematical reasoning in the mathematical induction part, if you can reason this part out, and you are always find it's very easy to do it. But if you cannot find this in some like number problem like this, it's not very worried about it, because you have a long time to think about it, not need to think about it in one night. You might use a whole week to roughly think about it, one day and another day. Okay. And the last topic we're going to bring about is the recursion. So recursion is, so mathematical induction is just one type of recursion, and recursion is based on the index set usually. And yeah, it's a statement that is true when input is I, and we can always describe p I plus 1 based on pi's if like pi is known. So it's like a formula. It's always look like formula if like pi plus 1 is equal to pi doing something, maybe plus a minus c something. So if we know pi, we definitely know it, and we know p plus I, and then we can know pi plus 2, because they are roughly doing the same thing. pi plus 2 is equal to pi plus 1 plus a minus c again. And this is we call recursion. It's like first only defining some fixed term like P1, P2, and we can use the P1, P2 to find P3, P4, P5, and P infinity. So recursion is a kind of like implicit process in mathematical cases. So we'll see some examples like the inductive case in mathematical induction is a recursion. Absolutely, because when we are only supposed like the k is true for all of the n between 0 and k is true. So which means like all of smaller term is true. And k plus 1 is true. Maybe here's k instead of n, but n is also makes sense. So, and then we can describe it. All right. And the second one is like someone takes a staircase to top from the bottom, like you are riding a staircase from the second floor to the third floor. Like this is second floor, this is third floor. And you are taking, and the information stored at each step is a recursion. So the information here, 0, is just a ground floor. And step 1 here contains the step 1 plus ground floor. So we'll see it here. So step 0. So we use a bracket to say, the bracket says, the round bracket here says like it's an information stored at each step. And if there's no bracket, we'll say it's just a step itself. Okay, so step 0 contains the information of the ground floor. And step 1 is the step 1 plus ground floor. And step 2 is step one plus the information stored in step 1 plus step 2, which is step 2 plus step 1 plus ground floor. And information stored in step 3 is information stored in step 2 plus step 3, which is the additional one. And if you write it totally, it's step 3 plus step 2 plus step 1 plus ground floor. Yeah, and it goes to step n, and it goes to even n plus n, n plus 3n, n plus so many, and it goes to infinity in this case. And the most common index that we're doing is the most common index set in recursion. So what is that? It's usually the natural number, I would say. Yeah. So most common index set y is natural number, because if you denote with rational number, it doesn't make sense, because how you say like you already have a0, and what's next? A 0.001. But you can always find a smaller one, so this is not the case. So maybe the natural number is the most convenient one. And so let's introduce like a common recursive formula. Addition, every step is the previous step plus something. Multiplication is an is equal to n minus 1 times something, times like the ratio r. D might be the difference, R might be the ratio, power. Yeah. So here we can only find like the an is defined only by the previous term, but here like an is described by the previous two terms, a n minus 2 and a minus n minus 1, and a1 and a2 is defined. So for all n greater than or equal to 1, we can, if we define a1 here, a2 here, so we can find a3, and for a2, a3, we can find a4, so it can goes forever. And this is one example of very famous example. It's called Fibonacci sequence, which is an equal to a n minus 2 plus a n minus 1, with a1 equal to a2 equal to 1. So which just means like so think about it, what is goes on. A1 is 1, A2 is 1, A3 is 2, which is 1 plus 1, and 3 is 2 plus 1, 5, 3 plus 2, 8, 5 plus 3, and 5 plus 8 is 13, 8 plus 13, 21, so it goes to infinity. this is the Fibonacci sequence and very common in math later. And the application of recursion is important because I'm studying statistics right now, and I'm using a lot of like machine learning techniques in prediction for large data-driven method. And I'm using RNN this summer, I think so. And recursion definitely is working it. We must take information back and do, and there's like some data driven into it, and output some data driven and doing the next stage. So it goes like that. So this is recursion application in computer science. So here I list some like symbol, summation, product, factorial. You just look at it. There's not too much to talk about. Yeah. So summation, you can write it as a recursion like that. So this is a recursion write method, and this is a direct write method. We call this one is implicit, and this is explicit. Okay, and the product is the kind of time together, and always the n times to n is an times ai from 1 to n minus 1. And factorial is you can write, and this is the implicit, this is the explicit. That's very similar. And just remember, there are some special cases. So if we dealing with 0, factorial is always defined as 1. But you may say, well, 0 times itself times to 1 is 0, but it's defined to be 1. Especially in combinatorics mathematics, we found this definition. This definition is the most convenient one. And if k is a negative number, then its factorial is undefined in this stage. Yeah, that's roughly about today. And next lecture, I think it's 2 days from now. We'll start talking about functions, which is more dynamic from what we talk about right now. Because you can see most of the example we're talking about is stationary. It never changes. The set is never changed. It's not like adding new element to it. It's not like a connection with other, which in a dynamical form. But next week we will.